for the invitation. There is one thing that I don't like about this scholar program, this word senior. But anyway. So as soon as I entered this complex, I realized that the title I gave to my talk, this how to get from A to B. I don't know how to, yeah, that's what it, this was really the right one. You see, I cannot promise that I can give you practical advice how to find your way in this building, but you can consider it as an allegory, because while you are going from A to B, you may have interesting mathematical thoughts, and that's really kind of the plan of my talk. So I am planning to talk about 4 open problems, maybe a little bit more than 4. Some of them will be definitely kind of, in my opinion, solvable. And they are interesting open problems in my opinion. And in the background, there is always some motivation from kind of computer science, where it is a very usual kind of theme that you have a configuration and you want to transform it into another configuration, and you want to do it efficiently by an algorithm. So I don't know how far I will get. So if I will stop after the 3rd problem, then there will be, it's interesting that it is switching all the time between me. I don't like to watch myself. So we'll see how far we'll get. So the first one is Mozart's piano moving problem, which is kind of interesting because I heard this problem as the piano moving problem, but in the last 20 years, usually it was referred to as the sofa problem. I think that you will see perhaps the reason in a minute. So the problem is very simple. The question is that you want to find the largest area region that you can move around in a corridor which has right angle turns, can turn to the left, can turn to the right. And there is an important condition that these turns are not too close to each other, because that may complicate life. So how big such a region can be? Obviously, if you take a unit square, right, then you can just translate it without tilting it through this corridor. So this means that an area, I don't know what's happening in the background, so I hope something exciting. So the area 1 is obvious, and the best construction so far was discovered by Romic. It's called Romic sofa. It's a strange kind of shape, not only for a piano, but also for a sofa. But it is conjectured at the moment to be the largest shape which you can push around along these corridors. It consists, you cannot see that, it really consists of 18 pieces, if I'm not wrong, and each of those pieces is an analytic curve, which is the solution of a differential equation. And most likely this is the best, but who knows? So what we know is that if you only want to turn right, then actually you can get a larger shape, and the area of that shape is bigger than 2.219, and this is Gerber's sofa. And this, you can imagine that you have a sofa like that. So probably that's why the problem changed its name. And now we know that, most likely, that this is indeed optimal. It was proved in a PhD dissertation by Jean Beck last year. You can read the dissertation because it is available on arXiv. It's more than 100 pages long, but it is very nicely written. And I had some correspondence with Jin about it, and he has no idea whether his proof would generalize to the problem when you can turn both left and right, because the proof is rather complicated. It consists of several steps, and I think it would be an interesting project just to see that what are those points that are critical, what are those points that can be generalized, and probably with some work one can also solve the original problem. Now, as far as the piano movers or sofa mover problem is concerned, it created a separate discipline within computer science, or if you wish, within robotics, which is called robot motion planning. And here I show this picture. On the left side, you see my good friend Michal Sharir, and on the right side, Jack Schwartz. When I joined Courant Institute, then they were leading a robotics laboratory there. And Jack Schwartz is really one of the brightest people I've ever met. He had books. First of all, he wrote the Bible of linear operator theory together with Danforth, which appeared in all possible languages of the world. But he wrote books about quantum field theory, about relativity theory, Marx economy, psychoanalysis, and he was one of the pioneers of automated proof checking and media, and so on. If he had concentrated his efforts on one area, I'm sure he would have gotten a Nobel Prize. At any rate, at that time, they got a big grant from DARPA, the US Army, and I can say that this robotics lab sort of created a lot of interest in mathematics, and also some algorithms came out of it, but luckily it didn't contribute to the creation of any weapons that can kill people, and I think that it was a wonderful institution. Now, let me try to explain to you the basic idea that Sharir and Schwartz had. So this is like a toy model of the problem of robots. So you imagine that, again, I will cover the picture, I apologize for that. So imagine that you have a number of, for simplicity, polygonal obstacles in the plane. They are fixed, and you have a robot. Imagine for a moment that the robot is also a convex polygon, in this case, this little triangle, and you are allowed to move this triangle, slide it, but you are not allowed to tilt it. And obviously, there are several questions you can ask. You can take the robot, and the question is that can you get from this position into that position without colliding with the obstacles? And the approach, which actually was also discovered and introduced independently at MIT at about the same time, was the following. That we put a handle or a point of reference in the robot. So we are moving this robot, holding it at this point, and then we see what happens. So first, so let me get a slightly bigger picture here. What we can do is that we can take this robot and we can slide around the first obstacle. And we see that what will be the curve along which, meanwhile, the handle, the point of reference will move. This is this red curve. So obviously, if we have a position of the robot where the reference point is within this red curve, then it will collide with the first obstacle. If it is outside, it won't. So in this way, we can define these extended obstacles, and we can do it for each of the obstacles. We get these pink regions. It's very easy to describe those pink regions if you know the notation of the Minkowski sum. So if one of the original obstacles is Ci, then the extended obstacles you calculate by adding to Ci the rotated 180 degrees rotated copy of the robot, and that will be the sort of description of the extended obstacle. Now, it turns out that, I mean, it's easy to tell whether you can get from one position of the robot, like the reference point is here, to this position. Well, in this case, you can get because they are in the same connected component, right? If they are in different connected components, there is no chance. And to get any kind of algorithms for this thing, you really need to say something about the complexity of the picture. And the complexity is that what will be the number of elementary arcs that the boundary of the union of these pink objects will have. And there is one simple observation you can make about the boundary curves of the extended obstacles. Any two red boundary curves intersect in at most 2 points. It's very easy to prove by hand. And then we prove this lemma, for which unfortunately still there is no really simple proof, that if you have a number of curves, closed curves, so-called pseudo-circles, so that any two of them intersect in at most 2 points, then the union of the interior is bounded by at most 6n minus 12 arcs. Yes, your feeling that here Euler's theorem plays a role is correct. 6n minus 12 is twice the number Cn minus 6, and this is really how the proof works, but the translation to this problem is not trivial. Anyway, for our purpose, the important thing is that it is linear. It's a linear. The number of arcs, the complexity of the picture is linear in n. And then, you know, by using divide and conquer, the usual tricks of computer science, you can come up with an algorithm in calculating with nearly linear time any kind of problems you can think about whether you can get from one point to the other to find the shortest path, and so on. Since then, I guess that one of the logarithms has been eliminated. So there is one expression I have to explain. So this white region outside of the extended obstacles, this describes the free placements. So if the point of reference is in the white region, then there is no collision. So we call it a free placement. Now, this question actually motivated and inspired a number of other questions that are very similar and that led to interesting mathematics. So what happens, for instance, if instead of this triangular robot or polygonal robot, a robot is just one sort of half line or whatever, one stick, which is infinite upwards, and the obstacles are n segments, and we want to know that how we can move such a sphere around if we are not allowed to tilt it. And to describe the possible movement of that sphere, again, we need to know something about the complexity of the picture. Perhaps it is a better way to describe this problem in the following way, that we imagine that there is the sun up there, very high, and here are our n segments. We label our segments arbitrarily, and then the sun will illuminate some subsegments. And what we are really interested in is the number of subsegments, the total number of subsegments illuminated. This can be larger than n because the same segment, like here, can have several illuminated subsegments. So one approach to this problem is the following, that we kind of scan this picture from left to right, and we always write down the label of the segment whose subsegment is illuminated. So here it is 1, then a part of 2 is illuminated, a part of 1 is illuminated, part of 3 is illuminated, and so on. So we get a sequence formed by these n numbers, and the sequence has two obvious properties. The first property is that two consecutive numbers are the same. This is just by definition. And the second one is that the sequence has no alternating subsequence of length 5. So no A, B, A, B, A. So when I say A, B, A, B, A, there are these dots here. This means that between this A and B, there can be an arbitrary number of other symbols. But there's no such thing. And this second condition, it's just a simple consequence of the fact that two segments can intersect only in one point. Actually, Davenport and Chinsel came up with this problem in relation to differential solutions of differential equations. And then the question is, our original question, that what is the number of illuminated subsegments, is just what is the maximum length of such a sequence, which is called the Davenport-Chinsel sequence. Because the number of elements here is the same as the number of illuminated subsegments. Now, there was a paper from 1974 written by Andres Emeredi, in which he proved an upper bound, non-trivial upper bound, which was n times the iterated logarithm function, which is a very nice argument. But the right order of magnitude was found later by Hart and Charir, who proved that the maximum length of such a sequence is just slightly superlinear. It's n times alpha n, where alpha is the inverse of the Ackermann function. The Ackermann function is this extremely fast-growing function, much faster growing than exponential, double exponential, triple exponential, whatever you wish. So its inverse is essentially a constant, but it tends to infinity. So in fact, it is so small that if n is about the number of atoms in the universe, then the value of the function is still under 10. So it's really not surprising that Atala in 1983 conjectured that this function is a constant. So you can also say that he was right. Depends, but it tends to infinity very, 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 very slowly. Now, so as a corollary, we now know that the number of subsegments is n alpha n, and we can have all kinds of algorithms how to move around in an environment determined by n segments in the plane. So the question which remained open, however, that what happens, which is much more important for computer scientists in higher dimensions. So in the 3 dimensions. So obviously the illumination problem is more interesting in 3 dimensions, especially if you are interested in computer games, because you want to be able to see if there is an environment what are those pieces that you can actually see from your viewpoint. So in 3 dimensions, for instance, a simple example is that you have triangles in 3 space. Again, you illuminate them from above. What is the number of pieces you get? And the conjecture is, prevailing conjecture is that as you go up with the dimension, well, in 2 dimensions, the bound was slightly superlinear. In 3 dimensions, you would conjecture that it is only very slightly superquadratic, and so on. The cubic upper bound is trivial in 3 dimensions. And in fact, in 3 dimensions, Charir more than 30 years ago proved a bond which is nearly quadratic, but not what was conjectured, that it is n squared times something which is really almost constant, which is like related to inverse Ackermann function. Now, I think that to solve, in higher dimensions, we know essentially nothing, and it's clearly we will need some good ideas, new ideas to attack this problem in higher dimensions, because all of those things that followed from the existing methods, actually you can find in a monograph of Sharir and Agarwal, which was published 30 years ago. Not much progress has been made since then. Okay. There is a problem which is closely related to that, which I'd like to mention to you. And this is the following. That imagine again that you have convex bodies in the d-dimensional space. The 3 dimensions is enough, but there is no big difference between 3 and higher dimensions. And you'd like to know that how many holes they can surround. What does it mean that they surround a hole? Well, you take those convex bodies, you delete them from the space, and then the space will, in many cases, become disconnected. And your question is that what is the maximum number of connected components that you can have? Now, if you are in the plane, then actually this it's not very hard to solve this problem. It turns out that the maximum number of holes that n convex sets in the plane can surround is quadratic. In fact, it is n minus 1 choose 2. And the best configuration is that you take n pairwise intersecting segments. Then it doesn't matter how you take them. It is a well-known high school exercise to prove that the number of pieces will always be exactly n minus 1 choose 2, unless I miscalculated it. But the interesting thing is that this quadratic number you can attain only if your objects, convex objects, are very longish. If they are not longish, they are fat. And what fat means is, for instance, they are circles, or you can say that the ratio of the radius of the circumscribing circle divided by the radius of the inscribed circle is bounded. So they are reasonably flat, like not very longish ellipsoids and things like that. Then actually, the number of holes they can surround goes down by n. So it will be only linear. So this was proved also more than 30 years ago by these people. And the pattern continues. In 3 dimensions also, the best you can do is cubic, and you can have these flat sort of, if you wish, infinite planes, or a finite part of it is enough. And then the number of holes that they surround will be cubic. But if you have balls, then it goes down to quadratic. And also, it has been proved by several people, mostly students of Sharir, that in 3 dimensions there are other objects like cubes or cylinders and things like that. Then also the truth is close to quadratic. The number of holes is close to quadratic. In high dimensions, all of those ideas sort of break down. But so this is not really satisfying. It's okay that there are nice results, but you remember in the plane there was a general result not just for balls, but for fat objects. So I'd like to have something like that. And the first conjecture was that if we have our objects are translates of the same convex body in 3 dimensions, then already the bond, it is like for balls. So why translates? Of course, those bodies can be longish. But even if they are longish, since they are translates of each other, those objects, you can squash the space. You can, elegantly saying, you can get a affine transformation of the space so that they become kind of fat, roundish objects. And then you would like to say that the number of holes can be only quadratic. The fact that it cannot be bigger than cubic is kind of clear, because if you look at a hole, then every hole has a leftmost point. And that leftmost point is sort of at the intersection of the boundary of three objects. Now, to the surprise of everybody who worked on this problem, in 2017, Aronov, Chong, Dobbins, and Clark came up with a counterexample. They came up with a three-dimensional body so that if you take n translates of this body, then they can actually surround a cubic number of holes, so the question which I think is doable is this question here. So in retrospect, it is clear that the main idea in this construction, which is rather technical, which makes the cubic bound possible, is that the convex body they construct is kind of asymmetric. So the new conjecture would be, my conjecture, but I don't take, of course, responsibility for it, but it appears also in this quadruple paper, is that such a construction is impossible for centrally symmetric convex bodies. So if you have n translate of a centrally symmetric convex body, then they cannot surround more than roughly a cubic number of holes, roughly a quadratic number of holes. Now, there is a side comment that I'd like to make. So what happens for unit balls? So for unit balls, it's very easy to prove, if you wish, by induction, even if the balls are not unit, that the number of holes is at most quadratic. So essentially, this follows from what I have said, because you can add by induction the balls kind of recursively one by one. And when you add a ball, it is intersected by n-1 other balls, but we know that the complexity of the complement of those n-1 circles, even if they were pseudo-circles, is also only linear. So if you add a linear bound, a linear number of times, then the whole complexity will be only quadratic. So, but one question, very annoying question remained, that what happens if we have unit balls? Can we really have a quadratic number of holes between any unit balls in three-dimensional space? And that I managed to answer together with Herbert Edelsbrunner. I don't know why I stated it in d dimensions, just, I guess, to show that the result generalizes, but let's see if d is equal to 3. And it says that we can have n unit balls in the three-dimensional space so that the number of holes they surround is n to the 3 half, upper integer part, which is n squared. And this is, as I said, this is tight. So so how do we proved it? This is just an excuse to tell you a general idea which I learned in the last 10 years, which is actually applicable here. It's a very simple idea, and it became extremely popular nowadays in data analysis. So how do you imagine data? The data in general, you imagine that a high enough dimensional space, you have data points. So A1, A2, and so on. You imagine that, for instance, each point corresponds to a patient or something like that, with all kinds of measurements. And So of course, my pictures are two-dimensional pictures always. So what you do is that you put in each of those data points a ball of radius r. So originally r is small, and then you start growing r. And you see what happens. And so what does it mean that what happens? So originally, of course, these balls are just isolated far away from each other. But after a while, there will be pairs of balls that touch each other. There will be triples of balls that have a point in common, and so on. And whenever there is a topological change in the picture, then you take note of it. And there will be finitely many such moments. And you want to record that. So there are many known constructions that are related to that. For instance, in the plane, you may know the Delaunay triangulation, which also you can describe in these terms. That's an interesting thing. It's also interesting that it gives a subdivision of the plane if the points are in general position. You have n points, and you take a triangle belongs to the Delaunay triangulation if the circle going through the 3 points doesn't contain any other point in its interior. And it's not difficult to prove that it really gives a subdivision of the plane or of the convex hull of all of the points. This is related to this. You can also describe it by this ball growing process. Now, by careful sort of bookkeeping, we can describe not only the number of holes that are sort of surrounded by these balls, but we can actually see those moments where each of the so-called Betti numbers change of this picture. So so what are the Betti numbers? Roughly speaking, it doesn't matter. So one of the Betti numbers is this. In the 3 space, the second Betti number is just the number of holes. That's exactly what we are interested in. And the first Betti number in 3 space is the number of kind of independent loops that you have around the union of these balls. So it turns out that there are 2 moments in this growing process, R1 when the radius is R1 and R2. So at some point when the radius is R1, then the number of loops in the picture will be quadratic, which is optimal. And there will be a larger radius for which the number of holes will also be quadratic. And the construction I just want to give you an idea how it will look like. It will look like something like this. This is a 3-dimensional picture. So you have a unit circle in the xy plane, and you take a point of it, and through this point, you take a unit circle which is perpendicular to the first circle. And here on this circle and on that circle, close to these 2 centers, you take m points or n½ points, very, very close to each other. And even this very simple construction is, if you look at the ball growing process, it is surprisingly difficult to analyze. But so I don't recommend this paper to be read or to be written, but it was. Okay, so now I'd like to switch to this Sam Loyd's puzzles. So Sam Loyd, I don't know if you ever heard the name. Believe it or not, 30 years ago there used to be a journal, Scientific American. There is still a journal with that name, but this is not what it used to be. So when in the Scientific American at that time, when quarks became widely taught at universities, then there was, for instance, a beautiful article that appeared about quarks, which was 40 pages long, explaining to the everyday person what quarks are. I think that today there is, in the New Scientific American, there is no article which is longer than half a page, because this is about the interest span of an average reader. So in that journal, there was also a mathematical column, and it was written by Martin Gardner, who often had mathematical puzzles that he stole, so to speak, from Sam Loyd, who was a very colorful person who lived mostly in the 19th century, and he was a puzzler, but as Martin Gardner puts it, he was also a hustler, which is true, and an excellent chess player. In his time, he was among the 20 best players of the world, and he had a lot of beautiful chess puzzles, and also he sort of wrote a book about tangram puzzles, in which he claimed that still many people refer to that the tangram puzzles, these are puzzles consisting of a small number of pieces, were suggested by a Chinese god under the name of Tan 4,000 years ago. Anyway, he also claimed until the end of his life that he was the inventor of the 15 puzzle, which you probably know, how you push around these little squares so that to put them in order. But that was a lie. It was actually patented much earlier than Sam Loyd made it sort of popular. And so anyway, that much about Sam Loyd's puzzles. And they inspired, again, some kind of an area in computer science, which is called this ugly name, metamorphic modular system. So what does it mean? I mean, those little squares of the 15 puzzle you can consider modules, and you want to push them around. Mostly people who are interested in storage and things like that, how to efficiently store things, they are interested in such problems. And so the general question is, again, let me tell you a toy model, and this is already an interesting one, that imagine that you have equal congruent coins, non-overlapping ones. Those are these shaded thing, n coins. There is a starting position, and they are unlabeled, and there is a target position where you want to push them. But you really don't care that which coin will end up in this position. So it can be this coin, or it can be that coin. This is an obvious algorithm for solving this problem in 2n steps. Because what you can do is that you can take the starting position, the real coins, and you can sort of one by one, starting with the rightmost one, you can shift them to far away. That's n moves, right? And then, but then you completely clear this area. And then one by one, you can bring them back so that the first one to the leftmost position, the second one to the second leftmost, and so on. And so these are 2n moves. In fact, 2n minus 1, because I guess that the last coin you don't have to take to infinity, but immediately you can take it to its position. Now, this problem, that what is the best algorithm, it's an unsolved problem. I am sure that it can be solved. But it gives me a good excuse to say something about, again, a nice piece of mathematics in which the other senior person, Noga, was involved. I don't want to count how many years ago. It's a beautiful theorem. The theorem is the following. You take n coins. They don't have to be such a nice position, just n non-overlapping coins. And your job is that you want to bisect them. What does it mean, bisect them? You want to have at most n half coins on one side, at most n half coins on the other side. You have to sort of sacrifice some coins because this line will intersect some of the coins. And the question is you are allowed to choose your favorite line, but you want to cut as few coins as possible. And everybody, I mean, this means me, would conjecture that the right answer would be square root of n. Although I bet that Noga also conjectured at the beginning that that would be the answer. But the answer is not square root of n. You cannot do it with square root of n. So you would think that if you densely sort of pack in a unit disk, kind of randomly but rather densely, then no matter how you cut through it, you have to cut square root of n coins if you want to separate them into two equal halves. And if they are not in such a nice way, distributed in such a nice way, but somehow more randomly or in a more longish region, or there are some holes somewhere, then you always find a direction in which it is narrower than square root of n. But no, actually the answer is square root n log n, and that logarithmic factor is needed. And in retrospect, it is clear for those who know that this construction that shows that actually you need the logarithmic factor is related to the famous Kakeya problem, which is that you have a unit length needle and you want to turn it around 180 degrees in such a small area as possible. And again, surprisingly, you can do it on zero area. So, okay, so this is one nice thing. And how can you use this? The way how you can use it is the following. Of course, I just give you the idea, and for the time being, I assume, which makes that previous beautiful remark kind of completely irrelevant, that the line that separates the coins into two equal parts doesn't intersect anything else. So n half coins are this side, n half coins are on the other side. And for simplicity, but that's absolutely not important, I also assume that the destinations, the target positions, the empty circles, they are also sort of nicely distributed so that half of them are on one side, half of the other side. And then you can do it in roughly 3 half n steps. You can move the coins into their final destinations, because what you will do is that you just take the coins that are on the right-hand side of the line, you sort of shift them away to infinity, right? Or far away. Then you clear the right side of the picture. Then you use these coins one by one, starting from the leftmost one and so on, to fill these positions. Maybe some of them remain unfilled. And then that's another n half steps. And then you take back those n half coins that are at infinity to fill up these empty positions here. That's roughly C half n. And then you can deal with the technical question of those coins that are intersected by a line. So actually, if you want to spell out the precise proof, it is a little longer, but that's the... But what's the best constant that you can sort of, achieve here? Well, there is a trivial bound, right? Because if none of the target positions coincides with a starting position, then clearly you have to move each of the coins. So you need at least n moves. And actually, it turns out that you need a little bit more than that, by a constant factor more. And here, there is also, very quickly, I want to show you a beautiful piece of mathematics, which was started by László Fejestót. So what is a stable packing? Stable packing of unit disks. So a stable packing of unit disk is that if you take any of the disks, you cannot move it because it is kept fixed by its neighbors. So, like here. But obviously, if you have the densest packing of disks, then you cannot move anything. But you can actually remove a lot of the disks, and it still will remain stable. And Fejestót's question was that what is the smallest density of a disk packing which is stable? So there is one very important observation, that a stable packing is always infinite. Because if you have finitely many coins, there will always be a rightmost one, which you can just slide away to infinity. So the question makes sense that what is the smallest density? So what is the density? You just take a huge, there are infinitely many disks, a huge circle in the plane, and you take the area which is covered by the disks, and you divide it by the whole area of the disk. And then Károly Böröczky, again a semi-infinite number of years ago, came up with a simple but very surprising construction that actually the density can be 0. And this is the construction. So what you see here is actually a construction which has kind of 3 infinite legs. And you would like to believe that those legs are like corridors with linear sides. But of course, they are slightly convex to make sure, you know, that if you take a coin here, or let's see here, then you cannot slide it to the left, because it's kept fixed by its 2 neighbors in that direction. So you can do it and then the idea is completely clear. You have to just work out the constant, because what you can do is, if you want to improve the lower bound a little bit, you can make such a construction using only n coins, which is kind of looks like you have the 3 legs, and then there is a triangular region inside. All of it are filled out with small disks, and these are the starting positions. And it is rigid, it is stable, except that from the end you can start removing things. But before you start removing things and you get into the triangle, you cannot do everything. So I will put the target positions inside the triangle in the middle. So you will waste at the very beginning of the process. You see, if you put the target positions, those red things inside, at the very beginning of the process, just to get any coin to its target position, you will lose a constant fraction of moves. So again, this is a question I am sure I don't think that many people touched it, that one can determine the best answer, or at least improve both of these constants, because it's not. And now I come to the last question I wanted to show you, this Kovaldzhi grasshopper problem. So this gentleman here is Alexander Kirillovich Kovaldzhi, who is even more senior than we are with Noga. But he's still, I think, that the deputy director of a famous school in Moscow, which is called the Vtoraya Shkola. The Vtoraya Shkola started in 1957, a long time ago, and he has been affiliated with that since then. He's a fantastic sort of problem creator. I think that only comparable to Sam Loyd, except that his problems are really mathematical. And in fact, I looked at this Moscow Mathematical Olympiad book, for instance, which he was one of the editors of this book. And I see that almost every year he poses on the International Olympiad, in Moscow Olympiad, like dozens of problems, and each of them is a sort of gem. Now, but the reason why I said that 1957, Khrushchev was the Secretary General of the Soviet Communist Party, and he wasn't a very well-educated person, but he thought that it can help the education if high schools are affiliated with industrial institutions. So there was a rule that at least technical high schools should have some partnership with factories and things like that. Now, the Vtoraya Shkola was at the center of Moscow. So you can imagine that how many factories there were in the neighborhood that they could establish some relationship with. But they came up with a wonderful idea. In the same district, just very close to that, there was the Institute of Precision Mechanics and Computer Engineering of the Soviet Academy of Sciences. It was wonderful. Today we would say that the Computer Science Institute, except that it was a very sort of rudimentary stage of computer science. And there were wonderful people like Dunkin and Gelfand and whatever who worked there. And strangely, the sort of the secretary of the education, they accepted this as a valid relationship. And these people started regularly visiting the school and giving lectures to talented students. And many, many talented people came out of that school. Two names you may know, Razborov and Tabashnikov, who himself is a very good educator. So one of the problem of Kovaldzhi that I would like to tell you is high school competition problem. It's a beautiful problem. Let me tell you the problem, and if you don't want to listen to the solution, then you close your eyes and ears and whatever. So imagine that you have n, or let's say 4 grasshoppers in the plane. And they are in some position, and what they can do is that one grasshopper can jump over another grasshopper and land at the same distance on the other side. And this step they can repeat any number of times. And the problem is the following. Imagine that you have only 4 grasshoppers, and those I show it to you because I worked very hard on this, and I didn't require any help from ChatGPT or whatever. Okay. So only 4 grasshoppers, and the 4 grasshoppers sit at the vertices of a unit square. And they start jumping. And the question is that you have to prove that they can never end up sitting at 4 points that determine a larger square. Okay, so now you don't listen and whatever the beautiful solution. I need to tell you the solution, otherwise, the whole thing doesn't make sense. So this is the initial configuration, right? So the first idea is very obvious. That you have to notice that, these 4 points kind of generate the integer, what we call an integer lattice, the integer grid. And no matter how these grasshoppers jump, they will always end up at a point of the integer lattice, right? Because if this grasshopper wants to jump over this one, this means that I translate it by twice this integer vector. So it will end up in another integer point. So no matter what they do, they will sit on this integer grid. Okay, that's fine. In the integer grid, there is no square which is smaller than the unit square, but it could be a larger square. And now comes the nice idea. No, it cannot be a larger square. And the idea is that because these moves are reversible, right? So if you take a move, this one jumps, this grasshopper jumps over this one, and we'll end up here. If I do it backwards, it's also a move. So if I have these movements, and I think of it as a movie, and I play that movie backwards, it's also a perfect, grasshopper jumping exercise. So imagine that, the grasshoppers start jumping, and they end up in 4 vertices, or that form a larger square, a square of side 2. But then, if I play this movie backwards, then in all of the positions, they will be sitting on a grid of side length 2. So I can never end up with the initial position where it was a unit square. So because of this, this is the solution of the problem. Now, immediately after hearing this problem, Kovaldzhi and Brunck, who I think is still a PhD student, maybe he defended since that, at IST, Austria, came up with a question that, okay, what happens if these grasshoppers sit at the vertices of a regular pentagon? And I finish in a minute. Can we do that or not? Is it possible to have a sequence of moves so that the 5 grasshoppers end up at the vertices of a regular pentagon of side lengths bigger than 1, bigger than the original one? And the answer is that yes, it is possible. And in fact, the previous argument that I described only works in the case when you have 3 grasshoppers or 4, as in the problem, or 6. In every other case, you can do that. And there is an obvious algebraic approach for that, which linear algebra approach. I just show you the slide, and I don't say much about it. It is clear what the approach should be, that you assume in any dimensions you have these grasshoppers, and they are points. Each point in d dimensions can be described by d coordinates. So if you have n points, this is a d by n matrix. And this describes the configuration, the original configuration. And what the original configuration, so the question is that what kind of final configurations can be achieved from this? And the approach, which I assume that if you learn linear algebra, you guessed, is that you have to check that what happens if you do an elementary step. And if you do a step when a grasshopper jumps over another grasshopper, then it corresponds to multiplying the configuration matrix by a matrix, by a very simple matrix, which is almost like the identity matrix with some changes. And you can actually describe what matrices, what are the set of matrices that can be generated by these elementary matrices that correspond to elementary movements. And they are called involutions, and that's very important, because if you take a move and reverse it, you apply it twice, then you get back to the original one. Okay. So where is the problem if we solve it? The problem is the following, that this whole involution business and the whole idea, which some of you didn't hear, the reversibility or whatever, it doesn't work if the rule is, that you have your grasshopper and it jumps over this one, but for instance, it ends up twice as far as it was originally. we didn't think much about it, but the method that we worked out definitely doesn't work in this case. Okay, so I, instead of entertaining you with further details about this problem, I go to the end, because you know I was supposed to give you an inspirational talk. Now I felt very bad about this expression, inspirational. So I thought that I cannot inspire, but I can find at least a quote of a person who you believe that inspired many others, at least in physics or peace movement, Albert Einstein. And this is what I found, that he really said that. I am not kidding. Logic will get you from A to B. Imagination will take you everywhere. So, you know, when I read this statement, I try to explain to you certain things which have more to do with logic. So I feel like more sympathize with the little grasshopper, you know, who has no idea what this is about. But I can only hope that it will inspire you. Thank you very much for your attention.
Thank you very much, János. So are there any questions? So any questions?
I answered all the questions.
Yeah, very good. Okay, well, let's thank János again for a wonderful.
Thank you very much for listening.